Okay, so in the last video, we introduced some terminology that we use when talking about computers, the CPU and RAM. Again, it's okay if you haven't heard those terms before, or maybe you've heard them but had no idea what they meant. That's okay. We're trying to introduce this stuff to you today because it's useful to think about as a programmer, kind of going on behind the scenes what your program is actually running on. What I want us to talk about in this video is thinking about a few more complexities that come up with how the computer is organized, and how this impacts the performance of our programs, so how memory is actually used. So I want us to think of memory by analogy of thinking of going out to the store. So suppose that there's some like essential grocery you need, and maybe you're not the best planner, and you have to go get it every few hours. So in this diagram, our essential grocery is bubble tea. So maybe you have to go to your favorite bubble tea place on the app, or off the app, whenever you get thirsty. And so whenever you have the craving for some bubble tea, you walk to the store, you buy some bubble tea, you walk back home, and you enjoy. But, I don't know about you, but sometimes, one bubble tea a few hours ago doesn't hit the right spot. Maybe you want some more. So you could, go to the store again, buy another bubble tea, walk home, assuming, maybe we think about this happening in a COVID-free world where you don't have to worry about going outside so much. But you could just go to the store as many times as you want. Now, if you repeated this multiple times a day, and it takes like 20 minutes to walk to and from the store, that's a lot of time spending away from studying 373. Now, we're being kind of wasteful here by going from your house to the store every single time we wanted a new bubble tea. Now, this might not be super clear how this relates to memory. We'll tie this in an example. But if you're a savvy shopper, you might know a way to speed up this process. If you know if you were going to make 3 trips to the bubble tea store every single day, why go to and from the store 3 times? Why not just, when you go to the store, grab 3 bubble teas? Oh, sorry, I guess this animation is grabbing a single bubble tea. Why don't you grab 3 bubble teas and bring them back and store them in your special bubble tea fridge? Maybe you have a dedicated, you're such a big fan of bubble tea, you have a dedicated mini fridge for that or something. So this is a way of optimizing your setup. You can go grab multiple things, probably more than you need at the time, assuming based off, past behavior, that I'm going to want more in a few hours. And that will save me time when I can just reach into the fridge and grab a bubble tea rather than having to walk to that 20-minute store. This idea of grabbing a little bit more than you need right now, knowing you're going to need it in the future, is a really core idea in computing in trying to speed up our programs. What we call this is caching, and it's spelled C-A-C-H-E, which is spelled really weird, but it's pronounced cache. And this is the idea of adding intermediate storage between your CPU, your house, and you, and the store, RAM. So even though I said RAM is relatively fast, and it is relatively fast, it still takes a while in comparison to the CPU. The CPU is spinning around really, really fast. And so any delay is actually a really long time for waiting for RAM. And so we set up these things in the middle called a cache. And the cache is going to store some of the extra values that you're going to grab just in case you're going to need them later. So that if you decide you have that craving for some data a few seconds later, you can get it more quickly without having to go all the way on that 20-minute walk to RAM. So this cache is going to store some small portion of memory that we can access more quickly. And so the communication time between the CPU and the cache is going to be really, really fast. But then if, for example, the value you're looking for, or maybe your cache doesn't have anything in it, then you're going to have to go all the way to the store, all the way to RAM, and grab it. So it's great if the data you're looking for is in the cache, but it might not always be the case. It's really just kind of a temporary storage in between. Now, how does this actually happen? Well, if we ever need to go all the way to RAM to, say, go to some index in memory to grab some value, your computer might as well make that trip count. So it already spent the 20 minutes walking to the store. It might as well, while it's there, just grab some more data than it needs so that if you ever need something nearby or you need something again, it should hopefully be stored in that cache. So your computer will automatically, you don't have to do anything as a programmer, it kind of happens behind the scenes. When you ask for a single value of memory, it actually brings back a whole chunk of memory. And it assumes that you're going to want memory in the nearby addresses, and we'll talk about why it does that later. But it's going to bring back a whole chunk of memory. So even if you just ask for a variable at this one index, maybe say index 114, it's really going to bring back addresses 110 to 117. We call this, we call this chunk of memory a block of memory, and it's just a big chunk of contiguous memory. Whenever you access one value in that block, it just brings back the whole block itself. Now, how does this, and again, this happens automatically. This is something the computer is designed to do really well. The whole architecture of the computer is designed around this concept of these memory blocks. And so this ends up having a major impact on programming when it comes to arrays. So suppose you're looping through an array, or you're just accessing an index. When you go to memory to grab index 0 or index whatever, it's going to bring back the whole block into your cache. It's kind of like, by default, instead of going to the store and buying one bubble tea, you realize that your arms were kind of made to hold lots of bubble tea. And so you just grab a whole armful of them and walk that whole thing home. The computer's architecture is designed to not grab single elements. It's designed to grab a block at a time, and it brings that whole block into the cache. So if you grab index 0, then when you go get index 1 the next time, you'll see that it's in your cache, it's in the mini fridge. And so you don't have to go all the way to the store. You save 20 minutes of time, and you can go back to watching this lecture, which is just so much better. So this is what we usually call a cache hit. You were looking for a value, and it ended up being in the cache because it already was brought back. And this works really well. These blocks of memory tend to be like a little big. And so if you have really small arrays, there's a good chance that the whole array will be brought back in that single block. So you really only have to go to RAM once for accessing a small array. Everything else will be stored in the cache. But it's okay if the array is too big, it doesn't fit in a block. Then once you run out of space in your cache, you'll just go back to memory and grab the next block. So that would be totally fine. Now, the reason it brings back the whole block is they're taking advantage of what we call locality. It's a tendency of programs to behave in a rational or reasonable way. So there's two types of locality that this cache system is designed for. The first is called spatial locality, and the second is called temporal locality. So spatial locality is the tendency for programs to access locations nearby recent locations. Lots of programs easily exhibit spatial locality. For example, if you're looping through an array, you first grab index 0, then grab index 1, then grab index 2. This block system is designed that it brings the whole block into the cache so that even if that first index still required going to main memory, when it came back and stored that in the cache, indices 1, 2, 3, etc., are going to be really, really fast. So spatial locality is all about accessing data nearby. If you're working with these contiguous blocks, it's likely that if you index I, you're going to soon be accessing index I plus 1. So it makes sense to grab the nearby memory. There's also this tendency that we call temporal locality, which is the tendency for programs to access data over and over again, or it's more likely they'll access data that it accessed recently. And lots of programs kind of easily exhibit this location. This locality. For example, if you're adding up values into a sum variable, it's likely on each iteration of the loop, you're accessing that one variable over and over again. That's temporal locality. You're accessing the same value again and again. And so programs that have spatial and temporal locality benefit the most from caching. Caching is designed to help these types of programs out. And the reason we talk about these things is it's important to think about when it comes to writing programs. So not only when we teach you how to loop over an array, we teach you to loop from index I to the end, not because that's the easiest to read, but because it's the most efficient. It makes so much more sense to do that than to jump around the array in some arbitrary order, like go to 1 and then index 17 and then index 2 and then some other thing. That jumping around would really slow down the program because it doesn't adhere to spatial locality. So this is one reason that we teach programming languages that kind of give you these building blocks to do these efficient operations. Now, not all operations in this computer are spatially or temporally local. So for example, think about how this memory model affects linked lists. Because the linked list nodes can be spread all over the RAM, they do not exhibit strong spatial locality. So for example, if I grab the first node, I want to access front.data, I might go to RAM and grab a big block of memory, but because there's no contiguous guarantee in linked nodes, there's no guarantee that the next value or all of the values are going to be in this block. And so here, it might be fine because we accessed, the first value. It's going to bring back all the nearby ones. We're okay. But then when I need to go to index 108 in RAM, that might not be in my cache. And so I'm going to have to go to memory again. So we don't get the same cache benefits when it comes to something like a linked list because there's no guarantee that the values are stored contiguously. There's no spatial locality here that if you access one value, you're going to be accessing something really close next because these things can be spread out all over memory. All the links can be all over the place. And it might not be included in the same block. So this is kind of the high-level picture of how data structures can actually, and how they're represented in memory, can impact the runtime, which we'll talk about in just a second. But this whole idea of caching can really optimize certain types of programs, but might not optimize for others. So far I've been telling a slightly simplified version of this story. It turns out that there's not just one cache, there's actually many caches that get progressively smaller and faster. There's the L1 cache that's really, really close to the CPU, but very, very small. There's the L2 cache, which is a bit bigger, but a bit further away. It takes a little bit longer to access. That's kind of everything above RAM that's stored between RAM and your CPU. And one thing I haven't really talked about too much is this idea of your hard drive, or your solid state drive if you have a slightly newer computer. So when you buy a computer, it has like 16 gigabytes of RAM or however much RAM you buy. And then you might also get a hard drive or a solid state drive that stores like 512 gigabytes or a terabyte if you can really go out there for an expensive laptop. I don't know how expensive laptops are now. I haven't bought one in a while. But that hard drive stores lots and lots of things. And that's where you store like your permanent files, like your poetry and your games and stuff like that, things you want to live on your computer forever. Now, this hard drive or your solid state drive, disk is what we generally call that term for both of those. That storage is huge, stores lots and lots of things, but it is so much slower to access. One of the benefits it does have, it's persistent. When your computer turns off, everything on your hard drive stays there, which as opposed to RAM, which everything gets cleared. That's why when your computer suddenly shuts down and you open it back up, all your applications aren't running like they were before because most of their state would be stored in something like RAM. All the important files like your settings and maybe your user files are stored on your disk, so those are still safe. But all of that stuff kind of lives in this slower area called disk. So I've mentioned, there's CPU and RAM, but there's other things to think about, like this cache in between the two, and then also this disk, this really, really slow, but very high volume and persistent storage. And actually, to give you a hint of why it's so slow, I mentioned there's hard drives or solid state drives. Solid state drives, SSDs, are a little bit faster, but not crazy faster. Hard drives, the reason they're slow is they're actually like little magnetic disks, and there's like a little arm that sits on top of them, and you actually have to wait for the disk to physically spin around to the right location and the needle to move to the right location, kind of like a record player, before it's able to read data. That waiting for physical parts of this like spinning mechanism to move takes so long from the perspective of the CPU, and I'll show you some examples later. One thing I should just quickly mention, we're not going to talk a huge amount about disk and how to access it, besides like that's where you store files. And actually in our next example, we talk a little bit about disk. But one thing you might hear out there is we sometimes call, just like how memory has blocks, people also think about disks having pages, which is the same concept. When you go to disk and grab some data, it brings back a whole page, which is like a really, really big block, essentially. So just wanted to mention that the terminology is out there, but you can think about pages and blocks being the same thing. Now, why talk about all this stuff? Why talk about caches and CPU and RAM and disk? It's because these storage locations have different latencies. What I mean by that is, in order to get data from one of these places, it takes some amount of time. And kind of having a broad sense of what things are fast and what things are slow are actually really important in the design of programs. So if you think back to what we talked about with algorithmic analysis, we used the tool of asymptotic analysis, and it told us that iterating through an array and a linked list are the same complexity class. They're both big O of n. And this is a true statement. Big O is a statement about growth rates as n gets really, really large. The growth rates are the same. They both scale linearly with n. And asymptotic analysis is a very helpful tool for quickly being able to identify these growth rates. But it turns out, because of this caching stuff and how memory is organized, most code that uses arrays, if they have the same big O complexity, will be much, much faster because there are significant constant factors that are faster due to how caches work. So this is one area that asymptotic analysis misses out. And I'm not trying to dig on asymptotic analysis. It's a really useful tool. It is explicitly designed to avoid this type of case. We throw away constants because we said that they're kind of untrustworthy. They might be too noisy. And we try to simplify things to give us a high-level picture. You can totally go on the other direction and say, what I really care about is counting the exact number of seconds this operation takes, which can be helpful, but can also be kind of hard because there's lots of noise in those measurements, lots of other factors, and so it might not give you as clear of a picture. They're just different tools. So one thing that is generally kind of, I don't think you should ever actually memorize these numbers, but sometimes it's good to see this diagram once of how long it takes to do various operations on your computer. So for example, if you want to go to that L1 cache, it takes 0.5 nanoseconds. And as a reminder, a nanosecond is 10 to the negative 9 seconds. It is very, very fast to access something in the cache. If you want to go to main memory, go to RAM, this suddenly is going to take you 100 nanoseconds. And I promise you, you are not going to notice 100 nanoseconds. But for scale, that's 200 times slower than accessing a cache. That is so humongously slow in comparison. And when you have to access RAM a lot, maybe you have an array with millions of entries and you have to access it every single time, those 200 times slowdowns add up really, really quickly. Now, there are lots of other latencies that they have on this diagram, but then consider this one for a disk seek. So actually going to a hard drive and waiting for that. That is going to take 10 milliseconds, which in the scale of nanoseconds is 10 million nanoseconds. That is 100,000 times slowdown compared to accessing main memory, which we already said was so much slower than accessing a cache. So this is a really monstrous amount of time you have to wait whenever you try to read a file or you have to go to disk. Now, one thing I should mention is that you don't always have to go to disk. It's only when you really read from files or certain operations. Most things on your computer, the things that you want to live forever, stay on disk. But a lot of your program state, like your variables and stuff, those live in main memory, and we're fine paying that 100 nanosecond cost to access them whenever we need to. And hopefully if we have temporal or spatial locality, we can access them more quickly in the cache. But this is kind of just a useful mental model of thinking. Cache, fast, memory, okay, not too bad. It's like a bit slower, like it's not ideal, but it's definitely not disk, which is waiting forever. And this is going to kind of motivate our data structure we're going to introduce called B+ trees. And to give you, I'll kind of reintroduce this in the next video, but the context here is when you're working with kind of obscene amounts of data that are definitely going to need to be stored on disk. There's no way you're going to be able to store it just in memory. And trying to optimize for this use case where going to disk is really, really slow. But I'm getting a little ahead of myself. We'll talk about these B+ trees in the next video.